Well, welcome back. This is the last segment of the National Training Center's Acid Rock Drainage Training Course, so we're pretty much in the home stretch. We've got a few questions and odds and ends that have come up in the last 15 minutes, so I'll go ahead and deal with those. And there are a couple questions for Jim, one of which is an estimate on cost for water treatment.
Well, I kind of anticipated this one. We recently had the same question just in the last couple of days, and what I can offer at this point, there are three different examples. One is an active treatment system at the Argo Tunnel, which we talked about a little bit earlier in Colorado. Now this is a 300 gallon per minute system. It's an average flow. I guess it goes up to 600 gallons a minute, I believe. And they're treating a total load, a metal load of, or at least let's say metal concentration of 311 milligrams per liter. Now, if we calculated a cost per 1,000 gallons, that would be $9.51 per 1,000 gallons. And that is just an operating cost. And that's based on 300 gallons a minute and $1.5 million a year in operating costs. This is a lime dosing system in Colorado. Let's take a look at it in a different way. If we took a look at the cost per kilogram of metal removed rather than on a gallon per minute, the number we get is $8.07. So for every kilogram of metal, we're looking at $8, roughly $8. Now, the passive treatment system at West Fork, which is that other the lead mine in Missouri, that's a 1,200 gallon per minute system, and it costs 700,000 gallons.
You know what it is?
Pardon me? It was a $700,000 to build, and the operating cost for that is 4 cents per gallon or per 1,000 gallons. 4 cents as opposed to the Argo Tunnel. But the metal loadings are completely different. But when you start and turn around and say, okay, how much does it cost on a per kilogram basis, the West Fork system and the Argo Tunnel system are very similar. The West Fork system is $10.80 per kilogram compared to the $8 for the Argo Tunnel. When I look at another site that we have been recently designing, this one hasn't been built yet, it's a 220 gallon per minute system for treating a very low pH, high acidity flow in Pennsylvania. The total capital cost is going to be about $1.2 million, and the total operating cost, say on an annual basis, will be around $50,000. Now this translates on a loading basis to 75 cents per kilogram of metal removed and about 43 cents per 1,000 gallons of water treated. And that water has a total total concentration. This is combined aluminum and iron of about 152 milligrams per liter. I don't know if that gives a feel for what these systems cost in terms of both construction and operating cost.
Well, I think it gives people some numbers and rough ideas that once you get into if you forget to do all the other stuff and you end up treating water, you're talking about some large expenditures. Mm-hmm. That's the most important thing. And speaking of large expenditures, we're gonna start off right now with a video showing some of the ongoing remediation work in Butte, Montana. Butte is the nation's largest Superfund site with an extensive array of ongoing remediation, and we're going to hear from Joe Griffin of ESE Harding Lawson, a consulting company with extensive experience at Butte, describing some of the work taking place. The situation at Butte essentially represents a worst case of not, quote-unquote, designing for closure, and that's a subject I'll talk about in a few minutes. But first, let's listen to Joe tell us about Butte.
This is the Berkeley Pit. It is at the upstream end of the largest Superfund site in the nation. It's also a major acid rock drainage site. To understand what went on here in Butte, you have to understand that it began as an underground mining camp in the 1870s. And underground mining basically needs to remove water from underground to enable the miners to keep deepening the mines. Butte eventually had nearly 10,000 miles of underground workings here when they started the Berkeley Pit in 1955. In 1980, the operators decided to abandon mining in Butte, and they shut off those pumps. The large cone of depression in the groundwater table that had formed began to rebound. That rebounding water table eventually reached the Berkeley Pit and now fills it as a lake. And that lake is continuing to rise. The main problem with this, of course, is that water has interacted with the sulfides in the underground working system and has become acidic. And that acid has released a lot of metals and other minerals into the water. And the Berkeley Pit Lake is now about a pH of 2.5 to 3. The Environmental Protection Agency has reached a record of decision, and they have determined that if they begin pumping that water before it passes a critical water level, they can maintain that cone of depression, which will also contain that 10,000 miles of workings and the lake in the Berkeley Pit. That water will, of course, have to be treated to standards before it can be released downstream. The biggest question that's usually asked about the Berkeley Pit and the flooding system is, why wait until it reaches a critical water level before they start pumping and treating that water? And there's really two parts to the answer. The first one is economic. And it is that if the people that are paying the bill can invest their money now, they will have more to pay for the treatment system later. The second part is that it's actually a form of treatment. It's a form of closing this mine system. It's called a wet closure in many places. So once you allow water to flood the mine workings, it will shut off the supply of oxygen and hopefully stop the oxidation process and the production of acid through the whole system. To understand Silverbow Creek, you have to understand that there were a number of smelters and mills operating right along the floodplain. The reason for that is that they needed the water to process their tailings. It moves the tailings easily out of the way for them. But the problem was that those tailings also were incorporated into the natural stream sediments. One particularly large flood, the largest historical flood on the Upper Clark Fork in 1908, moved a large volume of those tailings all the way to Missoula, which is 120 miles along the interstate and more river miles. But Silverbow Creek in this first section has now seen all the elements that will be required of the cleanup of the rest of the 26 miles of Silverbow Creek. And that includes removing the tailings out of the floodplain, rebuilding that floodplain and channel so that they act like a natural stream, and then planting vegetation all over it and getting the vegetation right so that it holds all of that reclaimed area together. I guess the vegetation is sort of like the glue that keeps it operating right. We're now located about 1.5 miles downstream from Butte. We're looking at an active zone of reclamation along Silverbow Creek, and this zone has all the elements that will be carried out all the way down Silverbow Creek. It includes initially removing the tailings out of the floodplain, then bringing in some clean fill and reconstructing that floodplain, reconstructing the stream channel itself, and that stream channel is designed to mimic what the natural stream would be in this area, a meandering stream. And then that will be finished off with the appropriate vegetation along there, which again will protect those new soils and will protect the stream banks. This same process will be carried out all the way down Silverbow Creek from Butte to the Warm Springs Ponds, which is a stream distance of about 26 miles. And it's expected to take about 15 years, although that's probably give or take 5 or 10. This site is located about 10 miles downstream of Butte. Behind me is a barren zone. It's devoid of vegetation, and those are streamside tailings. We also call those slickens. They are also the focus of much of the reclamation that will be done in this area. There's two major problems associated with these tailings. First of all, during the summer months, many of the metal salts are wicked up by evaporation at the surface, and they will actually form sheets of salts on the surface. They're fairly wet right now, so you can't see those salts, but often be yellows and greens from the copper salts. And the problem with those salts are that during rain events, those will be washed into the creek. And that has been one of the implicated in the eco-risk assessment as one of the major problems along Silverbow Creek and the Upper Clark Fork. The other problem associated with these streamside tailings is that they do generate small amounts of acidic water. It's locked up in the pore spaces and it only trickles out into the stream. But over 26 miles of Silverbow Creek, it does tend to cause chronic problems in the stream. This is the Warm Springs Pond system. It's located about 26 miles down Silverbow Creek. This is sort of the end of the Silverbow Creek story. The Warm Springs ponds were actually established by the Anaconda Company around the turn of the century. And they were placed here, the original pond was placed here to settle out the sediments that were being carried from Butte down the creek. In recent years, in the past decade, the pond system has been upgraded, the dikes have been strengthened, and lime precipitation process has been added to the system. That lime precipitation will remove the copper and zinc that are the main problems in the creek. Along with this upgraded pond system, an extensive wetland system has been established. As a matter of fact, it's now designated a wildlife sanctuary. This pond system will not have to operate indefinitely as they clean up Silverbow Creek and the Butte Hill. Eventually this pond system will no longer be needed, and Silverbow Creek will probably bypass it.
Well, that video should give you a good idea, a good perspective on what can go wrong when a mine is not designed for closure. Remember though, when Butte started, and for most of its life, there were no environmental laws, so that in that sense, this truly is a worst case scenario. We all hope that 100 years from now, a group of scientists are not sitting around in a similar setting discussing some of the mines that we've worked on. We've got just 2 short presentations left. With me again is Jim Gusick and Charles Buckham, and joining us now is Nick Rieger. Nick is a surface protection specialist from BLM's Washington office. He's going to tell us a bit about bonding and then say a little bit about closure. Afternoon, Nick.
Hey, Dave. It's nice to be here and talk about the regulations and acid rock drainage.
And before Nick launches into bonding, I'll hit Jim up with a couple more questions about treatment. One of which is, in terms of passive wetlands, how effective are passive wetlands in dealing with some of the more problematic elements like zinc, manganese, and perhaps arsenic?
Well, let's take these one at a time. The zinc is I don't think it's problematic at all. The highest zinc values we've ever seen that we treated passively were about 250 milligrams per liter. This is a pilot scale system that was operated in Cornwall in England. And again, we used a sulfate reducing bioreactor to take those to reduce those values virtually to non-detect. Manganese is something a little bit different. The manganese would be taken out in an aerobic cell, and there are lots of different mechanisms. There are over 13 different biological mechanisms that can be used to take manganese out, but some of the more common ones are algae. and I can give you the scientific name. Leptothrix discophora and Eulothrix are some of the common algae species that they actually use the manganese. And this all happens at pH 7. This is neutral pH water, as long as you've taken out most of the iron first. And this happens at pH 7, and these algae utilize the manganese in the water to actually, that's part of their life cycle. They make little barnacles out of it, microscopic barnacles, and they actually make pyrolusite, the mineral MnO2. And it's actually a good thing to have a little bit of manganese, because if you can drop it out, it provides a lot of absorption surfaces, and you can actually pull out other trace metals with it. So it's kind of Mother Nature's activated carbon. But again, you can take it out aerobically. Anaerobically is very difficult. And as a matter of fact, some of our anaerobic bioreactors, the sulfate-reducing systems, we actually strip out manganese when we first start them up. There's manganese sequestered in some of the manure and some of the sawdust, and we'll strip it out first, and then it basically becomes a non-issue, and it's polished off later on. Arsenic is the best way to take that out, we found, is aerobically, precipitating it, co-precipitating it, adsorbing it onto iron hydroxides. And we found that you need at least a ratio. You need some iron, obviously, to take out arsenic. And the ratio is about 5 to 1. So in other words, if you have 2 milligrams per liter of arsenic, you can can think about having at least 10 milligrams per liter of iron present in order to get virtually non-detect. This can take it down. This particular method can get arsenic down to very, very low detection limits. So those are the mechanisms that we found that work pretty well for these.
So it's really just a question of knowing what you've got and adding additional cells to accommodate that.
That's right. Yeah. And again, I'm not going to put out any one size fits all. Start out with a bench scale reactor, or even start out in the lab, verify that these things work, that you have the bugs available to do it, and just phase up from there and figure out what your retention times need to be.
Okay. I had a question for you regarding and the question is regarding what you feel might be the cutoff for using a moisture retention cover system as opposed to a moisture exclusion system.
Well, I think what's going to be driving that is going to be economics. I think that as you start looking at the moisture, let's just say the thickness of the moisture, the evapotranspiration type cap, as that increases and increases, say in a high rainfall area, that's going to be a higher cost. And then when you start calculating the cost of moving all that dirt versus looking at a different type of a design, say going with a moisture retent, or going with an infiltration type barrier cap, I think that's going to be really the driver in terms of which one will work. Because I've seen one design up in the Black Hills of South Dakota where they actually thought that they were designing an infiltration barrier cap, so with multiple layers and drainage layers, and then because of the low temperatures there, they put in a really thick, call it a frost barrier. And it turns out, at least my interpretation of the data would suggest that the high frost thickness, or the frost protection zone, is actually it was behaving like an ET cap instead. But I think it's going to be economics that drive it.
Okay. Thank you. We did have one fax that came in, and this concerns the Avarice system. That's I was impressed with Kim for being able to put together a question and answer on an ARD broadcast where the answer was airplane. And this relates to the Avarice land screening system. The questions are: is the Avarice land screening system available to state agencies? I believe that it is, and I believe it's contracted. You can contract, I'm not sure through whom exactly, but I do have some information coming up on that. And also cost per unit area and a website. I would refer, this is from somebody from the Arizona DEQ. Apparently, there's a paper in the ICARD 2000 volume, which may have some information on that. And I believe that the Utah BLM has done some avarice work, and a contact there might be Terry Snyder at the Utah State Office. If she doesn't have some information, I'm sure you should get some contacts for you. So with that, it's about time to turn it over to Nick for bonding.
All right, well, thanks, Dave. Well, in this session, I will be describing BLM's current policy in ARD, drainage based on the current 3009 regulations. So here we go. Okay, so what happened October 30th, 2001? Well, what happened was the final rule amending the 43 CFR 3009 regulations was published in the Federal Register and became effective on December 31st, 2001. This final rule suspended in part the rules that were developed during the Clinton administration. Those Clinton administration rules were published on November 21st, 2000 and became effective on January 20th, 2001. The portions of the rule that were suspended were replaced in whole or part by the old regulations that were in effect before the rules were developed by the Clinton administration. What does this mean? It means in terms of the ARD, the rules published on October 30th, 2001, for the most part left in place the rules that were developed during the Clinton administration. The current policy on ARD is as follows. The operator must incorporate identification, handling, and placement of potentially acid-forming toxic or other deleterious materials into your operations, facility design, reclamation, and environmental monitoring programs to minimize the formation and impacts of acidic, alkaline, metal-bearing, or other deleterious leachate. And the citation for that regulation is there on the slide. 1, you also must handle, place, or treat potentially acid-forming toxic or other deleterious materials in a manner that minimizes the likelihood of acid formation, and this is known as source control. If you cannot prevent the formation of acid, toxic, or deleterious drainage, you must minimize that uncontrolled migration of leachate, and that's called migration control. If source and migration controls do not prove effective, then you must capture and treat the acid drainage. Long-term or post-mining effluent capture and treatment are not acceptable substitutes for the source and migration control, and may only be relied upon after all reasonable source and migration control methods have been employed. The financial guarantees are found in the current regulations in 43 CFR 3009.500 through .599. The final rule authorizes BLM to require a trust fund or underfunding mechanism to ensure the continuation of long-term water treatment. CFR 3009.552 specifically states the following. The funding mechanism must be adequate to provide for construction, long-term operation, maintenance, or replacement of any treatment facilities and infrastructure for as long as the treatment and facilities are needed after mine closure. The financial guarantee must cover 100% of the reclamation cost, including any post-closure water treatment or other site maintenance. Financial guarantees must be adequate to cover the cost as if the BLM were to contract a third party. And Davis-Bacon wage rates for third-party contracts is required by law. And there's a website address there which will give you the Davis-Bacon wage rates for your area. BLM administrative costs need to be included, and they usually range from 15 to 20% and are set by our National Business Center in Denver. The acceptable forms for bonding instruments are as follows: surety bonds, cash, irrevocable letters of credit, certificates of deposit, negotiable United States government, state, and municipal securities or bonds, investment-grade securities having a Standard & Poor's rating of AAA or AA, insurance. The BLM will no longer accept any new corporate guarantees. Now for a couple of examples of long-term trust funds that the BLM used. Based on a 1991 EIS for the Barrett Gold Strike, located in the Elko Field Office in Nevada, there were some uncertainties based on the early modeling as to what the final pit water quality would be like, as well as from the impacts from dewatering the groundwater table. As a result, a contingency fund of $1 million was set up to mitigate any impacts not anticipated or covered by mitigation in the EIS. The money was placed in an interest-bearing account with the Bank of America. The Elko Field Office manages the account and receives quarterly statements. Modeling done for the EIS for the Phoenix project, another example, an open-pit gold mining operation located in the Battle Mountain district in Nevada, indicated that there would be potential for acid rock drainage from the proposed waste rock dump. The final EIS for this project just came out. Solutes draining through the waste rock dump could contaminate groundwater quality 60 years out after the startup of mine operations. Based on the information from Battle Mountain Gold, prepared a water management plan to mitigate the potential problem with contamination of the groundwater. The basis of the plan is for early detection and, if needed, hydraulic control of the groundwater system with extraction wells to capture contaminated groundwater. The water would then be treated to Nevada drinking water standards and injected into the groundwater system. Following review and completion of the technical report for long-term water treatment, another report was then prepared and reviewed and approved by the BLM, detailing the specific costs of all the components of the system. Costing included periodic costs for replacements of some of the components, like replacement of pumps. Based on the cost estimates, future average annual costs of $64,000 per year are needed for monitoring, and future average annual costs of $483,000 are needed for mitigation. At project startup, Battle Mountain Gold will post an interim surety of $1 million, valid for up to 20 years. The interim surety can be adjusted and must always be sufficient to fully fund the trust fund. In addition, BLM is requiring that a long-term trust fund be established at project startup and that full funding of the trust fund occurs no later than 20 years after the project's startup. In summary, the current regulations stress source control or preventing ARD from occurring is our first preference, followed by migration control. And as a last resort, BLM has the authority to require long-term treatment of ARD and adequate long-term funding to accomplish this. Thank you, and back to you, Dave.
Thanks, Nick. Well, at this point, I'm going to step out of my role as the moderator and talk a little bit about mine closure. Of a general introduction to the concept of closure, which is, did you design, permit, and operate with closure ultimately in mind? The idea behind closure, particularly if you've incorporated some of the things that we've talked about over the last few hours, is to leave a site with as little maintenance as possible, as little long-term liability as possible, and leaving the land available for whatever uses have been identified either through federal land use planning or whatever land use meets corporate objectives if the land is private land. So here are the objectives for this final session. Recognize long-term responsibilities and liabilities following mine closure. But really, you have to do more than just that. We have to plan for those responsibilities and liabilities from the start by designing for closure, permitting for closure, making sure that the operator operates for closure. Again, the first question we have to ask is, why is it important to recognize long-term liabilities and responsibilities? The answer to that question goes to the responsibilities of the permitting agencies and the mine proponents' differing responsibilities. In our system of government, it's the role of the agencies through administration of the various state and federal laws to protect the general public welfare. On the other hand, it's the responsibility of the corporation proposing operations to meet the expectations of their stockholders. That is, the people who've invested money in the company. In order to meet those expectations, the company should seek to limit long-term liabilities that might ultimately impact their responsibilities to their stockholders. You should be getting the idea that once we've permitted the mine, there are some real similarities in both responsibilities and liabilities. The Bureau's position is that the operator remains liable for problems that surface after the termination of operations and the release of the reclamation bond. That, of course, assumes that there still is an operator, which may not be the case, particularly given the potential long-term impacts of acid rock drainage. I'm reminded of Dirk Van Zyl's suggestion for holding bonds for ARD-related mine closures given the potential for really long-term treatment, as in the P word, perpetual. His idea is that really the only organization with a proven record of longevity is the Catholic Church. Now, I'm not sure what the church would think of holding bonds for long-term water treatment, but it's an interesting thought anyway. The mine operator will generally be unable to avoid some level of long-term liability for their operations, particularly for these large mines, which are really large industrial facilities. That's the critical nature of getting things right the first time. So when we talk about duration and limits, what are we talking about? This is the Argo Tunnel treatment plant, which treats water from the Argo Tunnel developed to dewater mines in the Central City area west of Denver. This plant treats 300 gallons a minute of contaminated water and was completed fairly recently at a cost of $5 million. It costs $1.1 million a year to operate, and Jim has alluded to some of the costs for treatment in terms of the cost per gallon and mass of metal recovered. It's designed to last for 20 plus years and probably includes various replacement costs as usual. We need to realize that many of the mines are large-scale development projects that can last 20 to 30 years or maybe even 100 years. Look at Butte and Homestake. So as large-scale industrial projects, these will likely require long-term maintenance for tens of years under the best of circumstances, and that includes even simple things like fences, signs, diversion channels, kind of routine stuff. When the project involves water treatment, the complexity and cost is going to go up considerably. The agency is responsible for developing realistic planning documents, preparing accurate environmental impact assessments, and probably most importantly, working with the mining company during operations to identify and address any changes in the environmental impacts from the operations. Almost all operations change over the course, and it's important to keep track of those and keep on top of them. This is all a part of effective oversight of the mining operation. Remember, once we permit it, it's our mine too. This might be linked back to your planning documents in some respects, or it may be impacts from mining have required modifications to the land use plan because the impacts are such that the land uses envisioned in the land use plan are no longer feasible. The post-closure land uses will have to consider the impacts on the mine site reclamation, ensuring that mine site reclamation is not compromised by land management activities. Since it's late in the day, we'll forego any real exercise on this segment, but here are some things we'd like you to consider. And this is from the standpoint of the land use, the land for BLM and Forest Service folks. What does your land use plan say about mineral development? Does it address cumulative impacts from several operations or from exploration activities? What does the EIS you've prepared or someone else has prepared for you say about ARD? Will ARD happen? Is it addressed? Is it bonded for? Have you included provisions for monitoring ARD? Does a mining company submission include provisions for closure? Does it include provisions for post-closure responsibilities? Does it include long-term water treatment or other long-term maintenance issues? What does the project look like when it's done? So those are some things to really need to think about in terms of mine closure. And at this point, we do have some time for questions, so if you've got anything stored up for any of us over the course of the day, go ahead and we'll take any phone calls or faxes in the time remaining. Hearing no questions. Do you guys have any final thoughts before we close up?
We're drained. This is an acid rock drainage course,
Yeah,
so we're drained.
Well, in that event, that about wraps up our time today. We hope that you've found this presentation informative. If you've got questions that weren't answered or you're too embarrassed to phone us or whatever, our email addresses are on the website, one of the two websites for the broadcast, and go ahead and email or phone any of us if you've got any questions. If you are interested in having this course satisfy your annual BLM training requirements as a certified mineral examiner, please email Michael Horn at the Training Center for our post-test. We'd like to remind all BLM satellite downlink coordinators to complete the standard broadcast viewer roster and fax it to the NTC immediately. Or you can use NTC's automated viewer reporting system on the NTC homepage at www.ntc.blm.gov/satnet. Thanks for watching. So long from Phoenix.
To help your office participate in future telecasts, see the BLM Satellite Downlink Guide and visit the NTC homepage on the World Wide Web. NTC's internet address is www.ntc.blm.gov. Transcripts of this program and other NTC broadcasts are available on the homepage. For more information on upcoming distance learning events, as well as traditional courses, call the Training Center at 602-906-5500 or visit the homepage. This broadcast has been a production of the BLM National Training Center.